Okay, more oxyhemoglobin dissociation curves. So it turns out that there are 4 physiologically relevant factors that influence the oxyhemoglobin dissociation curve. 2 shown here are pH and temperature. And to a first approximation, we're going to talk about these effects as shifting the curve to the right or to the left. So normal pH is 7.4. If we lower the pH, makes the blood more acidic, the curve shifts to the right. If we increase the pH, the curve shifts to the left. Okay? If we increase the temperature, the curve shifts to the right. Okay? So this graph summarizes the 4 factors that shift the oxyhemoglobin dissociation curve. And to try to make it easier to remember these, we're going to talk about what causes the curve to shift to the right. Okay? So if we increase temperature, the curve shifts to the right. If we increase DPG, the curve shifts to the right. DPG is 2,3-diphosphoglycerate. This is a metabolic product of red blood cells metabolism. If we increase the PCO2, it shifts the curve to the right. If we increase the acidity or decrease the pH, that shifts the curve to the right. How can you remember all these things? Just think about actively metabolizing tissue, like muscle, okay? The tissue is warm, it's producing a lot of CO2, it's producing acid, and DPG, well, that's a metabolic product, so it doesn't quite fit the paradigm, but anyway. So these things all shift the curve to the right, okay? And the effect of PCO2 on the curve is sometimes called the Bohr effect or the Bohr shift. Okay, so what is the effect of a right shift of the oxyhemoglobin dissociation curve? Okay, here we have normal pH, and here we have a right shift that occurs with lower pH. Okay, and so if we think we have blood coming from the lungs, and we go to this tissue, so we have blood almost saturated. We go to the tissue, and this is how much oxygen will be released. Okay, if we go to a tissue that has a lower pH, we're going to release an additional amount of oxygen. Okay, so a right shift of the oxyhemoglobin dissociation curve means that this tissue is going to get more oxygen. Okay, well, we said that the things that shift the curve to the right are products of metabolism. The more actively metabolizing a tissue is, the more it's going to shift the oxyhemoglobin curve to the right, and the more oxygen will be released to that tissue. Okay, so this works to our benefit. Okay, so we have blood coming from the tissues, it goes back to the lung, and we're right shifted, so the blood gets oxygenated, fills up with oxygen. Okay, but in the lungs, we shift back to the other curve because we're blowing off CO2, we're increasing the pH of the blood, and so we go back to our normal curve, so we take up a little bit extra oxygen there. So there are effects at both ends of the system, but the major effect is in the tissues, and the important physiological consequence of a right shift is that it facilitates oxygen unloading to the tissues. Okay, so that's oxygen. Let's talk a little bit about carbon monoxide. Okay, carbon monoxide, CO, one oxygen with carbon, binds to hemoglobin. Carbon monoxide is a colorless, odorless gas. It's a product of incomplete combustion. Every winter you'll read in the newspaper about some family who was killed at night by a malfunctioning, a poorly ventilated water heater that produced carbon monoxide. It's colorless, it's odorless. You can't detect it, but it's there and can be lethal. Okay? The problem with carbon monoxide is that it binds to the same sites that oxygen binds to in hemoglobin, the heme groups, and it also has 240 times higher affinity for these heme groups than oxygen does. So in a competition between oxygen and carbon monoxide almost always wins. Okay, and carbon monoxide does two bad things to the oxyhemoglobin dissociation curve. A site that has carbon monoxide bound instead of oxygen can't pick up oxygen. So this is going to lower it prevents oxygen binding, decreasing the oxygen capacity. It also shifts the curve to the left. And by doing these things, it can kill you if you have enough. So here we have our oxyhemoglobin, let's see. Okay, here's our normal oxyhemoglobin dissociation curve. Okay. Now, carbon monoxide's binding curve looks like this. Okay, it's incredibly steep because it has 240 times higher affinity. So this is going to be like, well, anyway. So very high affinity. So any carbon monoxide that's around is going to jump onto the hemoglobin. Okay, now we have two more curves here. One of these shows anemia. Okay, and this would be extreme anemia. So we have only 40% the normal amount of hemoglobin. Okay, but the shape of this curve is the shape of the normal blood curve. The hemoglobin in anemia is normal, but you just don't have enough of it. Okay, and then we have this curve with carbon monoxide, in which 60% of the hemoglobin has carbon monoxide bound. So we call that carboxyhemoglobin. Okay, and so this 60% that has carbon monoxide is not available to pick up oxygen, so the oxygen capacity is reduced to only 40% of what it was. Okay, so let's think about this. We start in the lung, we're full of oxygen, we come over to the tissues, and let's say we have, I don't think I have this. Oh, okay, darn, I didn't have to do that. Okay, so anyway, we have our normal blood, we go to the tissues, and this curve tells us exactly how much oxygen is going to be released, that much. Okay, here's the person with anemia, we go over to the tissues, okay, and we can see that we're going to release this much oxygen, okay? So the oxygen released is decreased in direct proportion to the degree of anemia. So if we only have 40% of the hemoglobin, we're only going to get 40% of the oxygen release that happened in the normal case. Okay? That's not good, but it's not so bad. Let's look at the person with only 40% of the hemoglobin is available because 60% has carbon monoxide bound. Okay, they go to the lung, they have a PO2 of 100. We go to the tissues, and only a tiny amount of oxygen is released. Okay, and the problem is that carbon monoxide has left shifted the dissociation curve. So this is like an allosteric effect of carbon monoxide binding tightly to this site, increasing the affinity of the remaining sites for oxygen, which in this case is a bad thing because we're in the tissues and we want oxygen to be released, but it's not because the curve is shifted way to the left. So this tissue is going to be hypoxic. It's not getting any oxygen, so the PO2 is going to decrease lower and lower, and finally it will get to be low enough that will release a certain amount of oxygen. But whether this will be enough is problematic. Okay, so those are the two bad things that carbon monoxide does. It lowers the capacity of the blood for oxygen, and it shifts the curve to the left, making the blood hold on too tightly to the oxygen and not releasing it. Carbon monoxide is a product of incomplete combustion. Cigarettes are little devices in which you can produce incomplete combustion and then inhale the carbon monoxide directly into your lungs. Smokers have 3 to 8% carboxyhemoglobin. Heavy smokers may have up to 15% carboxyhemoglobin. Of course, if you drive on the expressway, you're breathing carbon monoxide. So we all probably have a certain amount of carbon monoxide It'd be interesting to know exactly how much. Anyway, if you have less than about 10% carboxyhemoglobin, you probably won't notice any effects at all. 10 to 30%, headaches, nausea, CNS symptoms, and greater than 40% is lethal. So how do you treat somebody with carbon monoxide poisoning? Well, you can just let them breathe air that doesn't have carbon monoxide. And this is the time course over which carbon monoxide will be replaced by oxygen. They compete. Usually carbon monoxide wins, but eventually oxygen will replace it. So after 5 hours, 50% of the carbon monoxide is gone. Okay, well, if the poisoning is more severe, you may give the person 100% oxygen to breathe. Okay, now we lower the 50% point to 1 hour. So in 1 hour, you've gotten rid of half of the carbon monoxide. If you have a hyperbaric chamber handy at 2.5 atmospheres of oxygen, you can decrease the time again by about half. So in about 30 minutes, you've gotten rid of half of the carbon monoxide.